All right, Erlan, really quick, I want to go through this last problem that we didn't get a chance to hit yesterday. So when we have something that reads like this, measure of whatever this sign is, right? Kind of looks like a weird shaped L, or an L was like this. It's just shifting it off, right? So this is an angle, right? So if you imagine that you had a triangle, right? And this is the angle. That's what it's showing here, okay? So this is an angle. So the measure M of an angle DCB, right? And we have points on here, A, B, C, and D, according to what you were given. So starting with the first letter, we have D, C, B, where C is the vertex here, right? So it's the center point here. So this is where the angle is going to be measured, right? So the question that's being asked is the measure of the angle DCB equal to, question mark, the measure of the angle BCD. The measure of the angle here is always going to be the same, right? When we're looking at a geometric object like this, right? When the center and the outside points are the exact same, doesn't matter what order they're in. So yes, this is true, and we can erase this question mark. Now, the next thing here, and I just took the points that he wrote on the page, starting from the top, going to the bottom, and I'm just going to try to go through them one by one here. So again, the measure of the angle ACB, so A, C, and B, right? So it's like a straight line, but we do have 3 points here. So the measure of a straight line, right? If we took a straight line, let's take a look at something like this, right? This is a right angle. This line, we'll call this PQR. So PQR. So PQ, the line segment PQ, is perpendicular to the line segment QR, right? So if I was going to write that, I'd write it like PQ, line segment, right? This means line segment or array is perpendicular. I'm actually going to write that in yellow just to show you the different symbols here, is perpendicular to R, the line segment QR, right? These line segments or rays are perpendicular to each other. Now, when I have a straight line, like I do here, ACB, what I have is 3 points, and I basically have 2 perpendicular angles here, right? So 2 90-degree angles. So when I have a 90-degree angle over here and a 90-degree angle over here, those add up to give me the degrees of a line. Now, what I have here are measured in radians instead. So what's a radian? So if I was going to take a circle, right, and say, all right, the radius of the circle is halfway, or half of the diameter, or halfway across the circle, half of the longest line segment across the circle, the diameter over 2, the radius is equal to half the diameter. So from the center of the circle to the edge of the circle, from the exact center to the edge of the circle, I have the radius r. And if I was going to take this radius r and say that r is equal to 1 unit, whatever that means, and then take another radius r, that being the same exact length, again, 1 unit, and then I was going to compare that to the distance between these, and if this was also 1 unit, this is where radians come from, right? So I have a radius and a radius here, and the distance between these 2 radii is going to be another 1 unit radius. So it's equal to the same thing, and this is where radians come from. And I know that's a bit of a haphazard definition, but it comes from using circles, and you'll see that in trig and in geometry. When we're talking about the unit circle, we're going to be using radians more. And the radius is equal to, sorry, I should say the radius so the radius is used and necessary to understand the circumference of the circle, right? This all kind of ties together. We can go over it more in session. don't want you to get too bogged down on this right now. But just understand that radians have to do with the arc length of a circle, right? The arc length is this on the outside of the circle. We can't call it like a side length, so we call it an arc length. And it's also relatively, obviously, involved with finding the circumference of the circle, right? And when we do that and we find this entire length all the way across here, what we have is this is equal to pi, right? Because if I had 2 pi r and this arc length is equal to 1, then this would be, I'm sorry, that's not right. If the arc length was equal to 1/2, then this would be equal to just pi. So in this case, we're just going to believe for a second that the radius is equal to 1/2, just for this example, so that we can get the circumference equal to pi, which is what we get in radians when we measure 180 degrees, right? So radians are just another way to measure angles, particularly with circles. So pi radians, the angle ACB equals pi radians. And we can go through the logic behind this a little bit more. It might be a little truncated the way I'm describing it now. So this is also a true statement. Okay. Now, if we go on to this number 3 here, so the measure of angle BCD is less than the measure of the angle ACB. So let's locate the angles B, C, and D. Okay, so that's a 90-degree angle. If this is to be trusted, and it is less than the angle of measure ACB. So the measure of ACB is going to be this angle, right? And we already know that this is 180 degrees, or aka pi radians. You'll see radians abbreviated as rads. So the measure of BCD is obviously less than the measure of ACB, because this would be measure of angle BCD in radians would be pi over 2, is less than the measure of angle ACB, which would just be pi, based on our previous true statement there. Okay, so what your teacher was trying to do here is walk you through a proof, but he didn't really explain it from what I understand. All right, and don't get confused here with this. That's why I wrote it in white initially, and the angle measure. So the measure of an angle is a very different symbol from the inequality. They do look very similar, but they mean very different things. Okay, so going on to 4, the ray or line segment CD, okay, here, is perpendicular to line AB. Okay, cool. So this should have come along a little bit earlier in the proof to justify some of the rationale that we had a bit ago. But I just want to point out before we get into that this is a line. This is the way that we denote a line, 2 points, and then the 2 points that we're noting here. So here it's A and B, so we're skipping C, is perpendicular to the ray CD. Okay? And that would have to be given. You can't assume that based on this. That would have to be something that's stated, whether directly or just with this little box here that we talked about when we were talking about special right triangles. So that would have to be something that is given to you. And then finally, what we're trying to figure out here is the measure of angle ACD is equal to what? Okay, in radians, the measure of angle BCD, so this guy is less than the measure of the angle ACB. So this guy, okay? So what is the measure of this angle? So in radians, we already know that, based on an earlier statement, mathematical statement, that ACB is equal to pi radians, okay? So we're going to take that, say pi radians, okay? And I'll put the measure of the angle up here, so ACB. Measure of angle ACB is denoted by pi radians, minus, what are we trying to find? We're trying to find this angle ACD, okay? So what we're going to do is subtract from ACB, this line, this angle, B, C, and D. And from the previous mathematical statement, we know that BCD is equal to pi over 2 radians, aka 90 degrees. So BCD here is equal to pi over 2 radians. So that means that the measure of the angle ACD is equal to pi over 2 radians, right? Because if I was to take pi radians, another way I can write that to find a common denominator with pi over 2 radians is by saying, all right, this is 2 over 2, right? 2 over 2 is 1. This is the same thing as 1 pi, right? Or just pi. So 2 over 2 makes that equivalent. Sorry, it makes it a common denominator. So if I take 2 pi over 2 minus pi over 2, right? And I get 1 pi over 2, which is the same thing as pi over 2. Okay? So going back here, that's why the measure of the angle ACB minus the measure of the angle BCD, ACB minus BCD, is equal to ACD. So this is equal to the measure of the angle of ACD, which is what we're trying to find right here. So the answer is going to be pi over 2 radians. Now don't forget your unit here, right? The radians is the same thing as saying, all right, 90 degrees, right? If I left off that 90-degree sign, then I just have 90, and it wouldn't make a whole lot of sense. What's 90 actually being applied to here? Is it the length of the ray or the length of the line, or what? The length of this line segment between C and D? The unit is massively important, especially when we start distinguishing between radians and degrees. So just a little bit of a heads up with radians. If I have pi radians, that's going to equal to 180 degrees. If I have pi over 2 radians, this is going to be equal to 90 degrees. If I have 2 pi radians, it's going to equal 360 degrees, right? So 2 times this up here, okay? And you're going to start seeing these more and more as you get into the unit circle. All right, so that's all we have for right now. I hope this elucidated this a little bit more. We can definitely go over radians, unit circle, a lot more in session, okay?